Okay, next bit of 2016 question 7. State 2 desirable physical properties of the fluid used in a heat pump. Yeah, that's it, sorry. State 2 desirable physical properties of the fluid used in a heat pump. Okay, so we want a low boiling point. Because we want it to boil relatively easily. We don't have to increase the pressure too much to get it to boil. We want a low boiling point to start with. And what do we want? We want a high specific heat capacity. That means as it boils, as it turns into a gas, it is going to take in as much energy as possible. If we just have a look at the marking scheme, what else they say? Volatile. That's another way of saying low boiling point, low molecular mass, little intermolecular forces. All kind of same points to the low boiling point. This is a very important point. We want it to absorb as much energy as possible when it does the change. Okay, very last bit of question 7. So on 2016, the fluid in the heat pump of a refrigerator has a specific latent heat of vaporization. Okay, that's our L of 4.6 megajoules. Mega is 10 to the 6 per kilogram. The internal volume of the fridge is 0.6 meters cubed. The heat pump removes 12 kilojoules of energy. So the amount of energy it's removing is 12 by 10 to the 3 joules from the air in the refrigerator as the fluid evaporates. Calculate the mass of the fluid that has evaporated. Okay, the mass of the fluid, we know that the energy required to change something's state from a liquid to a gas is ml, mass by liquid. So the mass is just rearranging this thing, all right? So mass is the energy divided by the specific latent heat of vaporization. So the where am I going? 12 by 10 to the power of 3 divided by 4.6 by 10 to the 6. 12 by 10 to the 3 divided by 4.6 by 10 to the 6 gives me a mass of 0.0026 kgs. Getting a bit tight there then. 0.0026 kgs. Okay, and then we have to calculate the fall in temperature of the air in the refrigerator. Okay, so I know I'm going to use E equals mc delta theta. I know the E, the M, the fall. Okay, so I'm going to use E equals mc delta theta, rearranged to be delta theta is equal to E over mc. That's the specific heat capacity of the air, isn't it? No, that is... What is it that I'm dealing with here? That's the specific heat capacity... Yeah, because the air is losing the temperature. Yeah, so that's the specific heat capacity of the air. Do I have that in the... I do, it's at the bottom. Look at that. That's a nice little hint. 1005 joules per kilogram per Kelvin. The energy I know, that's this 12,000 again. The mass of the air. I need to know how much air is inside the fridge. What else did they tell me? They told me the volume of the fridge, and what's at the bottom of the question is the density of the air. Lovely. Okay, so let's go over here for a second. You see this? You can. All right. Density is mass over volume. What do I want to know? I want to know mass. So mass is density times volume. That means mass is the density of air, 1.23 kilograms per meter cubed. And we know we've got a 0.6 of a meter cubed. So I can go back over to here now and say that the change in temperature of the fridge is the 12,000 divided by the mass, 1.23 times 0.6. I haven't worked it out yet, but I will work it out in a second. Times the specific heat capacity of the air. Where's that gone again? 1005. Okay, right, we're on to something here, I think. So I have 12 by 10 to the 3 divided. Give myself some brackets here so I can work all this out. 1.23 times 0.6. That gives me the mass times 1005. Close all that off. And I am getting a drop in temperature of 16.1 degrees Celsius or Kelvin.